Hello, everyone. This is Rick Arthur from GE Global Research, and we're going to have the next installment of the GE Software Webinar Series. The topic for today is supercomputing for engineering and scientific discovery. As you can read on the startup slide, if you have any questions during the presentation, please message Rebecca on the WebEx interface, and we'll probably focus on the questions at the end, but feel free to have them accumulate. We'll collect them up. We also will have a Twitter following the conversation as well. So I'm here today with Brandon Moore from my group, and we're employees in Niskayuna, New York, of the General Electric Company's research arm, and I manage a group called the Advanced Computing Lab. Brandon works in my group and has the logins to some of the top computers in the United States, and so he'll be able to talk some about those experiences as well. So what I want to talk about today is, first I'll give a brief overview of the Research Center itself, and then what we're seeing as a shift in computing, a shift in engineering and science. Then I'd like to share some rather stunning art that has come out of scientific visualizations that we've done, talk about software challenges that this problem area faces, some of the impacts we've seen to industry, and then we'll wrap up and have questions. So the GE Research Center was founded 1892. It's been around for quite a while. It's one of the longest running, most successful companies. In fact, was the only company that survived the Dow Jones Index for its entire history to now. We're quite a large company, and we do a wide variety of products and services. The lab itself is in upstate New York. It's the first U.S. industrial lab, and we have chemists, mechanical engineers, electrical engineers, physicists, biologists, computer scientists, quite a wide variety of people that work here, and that diversity needs us to be able to work on some very compelling problems in a cross-disciplinary way that's not available in many other research institutions. Our site is the oldest of the GE research sites. We have also opened sites in India, China, Germany, and we have one underway in Brazil. And relevant to this conversation, we do have a recent acquisition in our facility of a Cray supercomputer that some of you may have heard about. So we're investing in this area and have a lot of belief in this as a way to progress science and engineering. So I want to first just talk about computing technology and some of the trends that are leading us to the kinds of work that my group has had to do to enable this. So many of you have probably heard of Moore's Law, and this isn't Brandon Moore's Law, this is Gordon Moore's Law, which is famously predictive, even from back in the 60s, of a improvement in technology driving computer capability. However, Moore's Law, as displayed in this graph here, is talking about how many components we're able to put into an integrated circuit. It's not what other people have come to interpret that, and I'll talk about that throughout here. So this slide from the UT-CS department, and that's a log scale on the y-axis, shows how over time we were in fact able to see dramatic increases in computing performance through various technologies, but that in around 2002, we saw a slowing of this progress, and this increasing gap has led to a variety of approaches to try to maintain the trajectory that we were on, some effective, not so effective. So computing is in a bit of trouble. Moore's law is okay, but Moore's law is about feature density. It's not about performance in the classic sense. I will qualify that in a moment. Now, feature size is shrinking as expected. This is technically what Moore's law has been talking about. This is the ITRS projection, and they are in fact shrinking dies, growing the number of components that we can put into the circuits. However, many of you have probably noticed that the clock rates have not increased, and this graph shows Intel and AMD's CPUs, and right at the end you see a dip, and this was when we started into multicore. So what happened there was industry had to move from an old model of improving clock speed with each generation to now moving to still exploit the increased logic density, but to split the chip into multiple cores. And this has to do with some of the thermodynamics at hand on these dies. But what it means for us is a change in how we structure these programs. There's also something called Rock's law that addresses the complexity of designing these monolithic single cores, and that going to multi-core allows more simplification in those designs as they replicate cores on the same die itself. The other option was to specialize, and these were driven by really consumer segments, whether it's the cell phone market or the video game industry. And then this required a different structuring of how you would do processing and computation, and rewriting software to accomplish that. The problem is that if, in fact, your software is not written to take advantage of these, you are only going to see impact on performance that is commensurate with the number of threads or parallel paths that you're able to take. It's called Amdahl's law. The other problem that we're faced with is looking at the divergence in speed that CPUs have seen versus what memory has been able to keep in pace. And this is what's called the von Neumann bottleneck from the von Neumann architecture separating processor and memory, where you may have a chip that runs fast, but it's just not able to get enough data to process in this amount of time that it has. Another dynamic, and I borrowed a few slides from a friend and colleague, David Keyes, from Columbia, now at Kaus, where if we look at the Gordon Bell Prize, a very prestigious award in the computing academia and industry given out by the ACM, if we look at the cost per megaflop of the awardees of this top performance prize each year, we see a dramatic drop, even ending in 2001, and it's continued since then. And he's made a great analogy in how much this has impacted how we choose to use computers, in comparing it to the jar of peanut butter here. So if we take a similarity in cost reduction, and this isn't, and the one that we see in computing is even more dramatic than this. we make sandwiches with it at the $3.20 per jar. As it gets cheaper and cheaper, we start looking at it as a use for fuel, or even paving roads when it gets really inexpensive. So what I refer to here is the commoditization of terascale or gigascale or exascale. Take your pick. As these become more and more affordable, we're going to be able to employ these in more and more mundane applications. The other thing that the advancement in computing is making available are what I refer to as an abundance of petascale. And this is making ample slots for terascale applications and programs on some of the larger machines that are now available at the national labs and larger institutions. But in order to do this, we need to address some technical challenges, like develop new hardware architectures to allow affordable purchase and operation of these machines. This includes thermal properties and power. We need new computer science to think again about the algorithms that we are developing, where the bottleneck has shifted and latency and locality become increasingly important in designing how we are modeling the problems that we're trying to solve. And we are being forced to conceptualize these first in parallel rather than come up with a solution and then figure out how to parallelize, since parallel is so essential. Additionally, as we get to these greater and greater scale machines, reliability becomes more of an issue, and we need to think about how to efficiently checkpoint or otherwise recover from bit errors or communication errors that may occur in the computation, which is far more likely when you're moving to tens of thousands or hundreds of thousands of parallel threads. And traditional data structures may not map at all to these architectures, so we need to think about those. As far as new applications, just even creating the input files and managing the output files that may be hundreds of terabytes or even petabytes in size is going to require new kinds of software. And last, human-computer interfaces. How do we ingest, understand, focus our attention, and get insight in the absolute deluge of data that comes out of these systems? So engineering and science has for years relied on basic scientific method, as illustrated in the top right, where we just iterate between forming a theory and testing that and refining it. So for tens of millennia, we've used experimentation, and if we're two tribesmen and one of us eats the red berries and the other eats the white berries, and the one who ate the red berries keels over, will probably continue to eat the white berries instead. And so experimentation is pretty fundamental to everything that we've done. And in fact, today it's really the best way to validate that everything is working according to nature. Theory really evolved with the Greeks in areas like geometry, or Newton with gravity, and being more of conceptual exercises. More recently, we've been able to employ simulation, where we think about applying computational models as an instrument to see what we cannot otherwise see. This is like a new kind of telescope or microscope. A great example of this was the Gordon Bell winner from that was run on Livermore's Blue Gene machine, where what we're looking at here is an alloy. This is an atomic model, and because of the size of the machine, historically they had only been able to model what you see in the darkened triangle or square in the top left. These are that one was representing about 64,000 atoms, and they had to tile that across to get the same volume that you can see in the lower right, which is 16 million atoms. And you can see that what we have artificially created through that tiling in A, B, and C here does not really resemble what we're seeing in D. And this is a great example of where scale has allowed us to visualize far more accurately what's actually happening in nature. But there are challenges in accomplishing all of this. Experimentation is fraught with cost and time restrictions. For example, in our aviation business, when we do a rig test, and it's like test for fan noise or a bird strike, we are talking about taking years to set up a new experiment or months to, if it's already existing. It costs millions of dollars to set up such tests. The analysis time of those results that are measured can be months to years. Each time that we do that, we need to machine new parts, check for repeatability of the rig, even look for things like oil leaks and such, and we need to freeze the design during that test. You can certainly imagine how being able to do this in a virtual form would allow for a much quicker and much more repeatable manner if, in fact, we can trust the results. And that's the validation piece. So I'll talk about that in a minute. But as far as the other things that are listed here, these experiments may be too dangerous. We can't really do a climate experiment where we melt the polar caps or something like that. The ITER reactor in France is a $5 trillion, I think, dollar expense, and that's something that we need to do once. They may be controversial, things like drug toxicity, where we can't really ask people to ingest something that we know to be harmful. It may be prohibited by treaties, such as weapon tests, and this is really what gave rise to the Department of Energy Labs programs. And they may be just difficult to instrument, especially destructive tests. Simulation, too, is limited by economics, confidence, and technology. So from an economic standpoint, you need access to computing hardware and software that can adequately run your problem. Confidence, you need to trust that the computer model, or at least know the limits of its wrongness. And then technology, while progress in parallel machines have helped certain types of problems, there are other types that it hasn't particularly helped. For example, those with long cause and effect chains, where causality is a strong factor. So our ability to map real-world problems to computer models in a solvable manner presents a challenge. We also have what I refer to as the multi-scale problem, and here we have three axes, and I've seen people come up with even other axes, but on the in the y direction, you can look at the accuracy and fidelity of it, whether it's stochastic in the sense of being a approximate model versus on the upper end saying that it's actually using basic first principles equations that we know to be true. In the x direction, we can talk about granularity, and here I've illustrated in three different ways. There's, if you look at the blue on the bottom, going from atoms to molecules to microstructures up through components to a full system. That illustrated to some degree in an aircraft engine, as shown in the red, where we talk about a blade. That's one of the spokes in a engine. To talking about the row, to talking about multi-stage, to the entire turbine. Or in biology, think about doing simulation at the molecular level, and then inside a cell, then an entire cell, then multiple cells forming a tissue, and the tissues being part of an organ up through the body. And it's really the interfaces and understanding how something at one level interacts with something at the next higher level produces an effect that's meaningful to your simulation. And then scale sequencing, what I mean by that is just how you do things on one degree of granularity versus another degree of granularity. And then the z-axis one coming down to the bottom left is just the scale of your problem. When we talk about grid points, you'll see some meshes later. 15, 20 years ago, we would describe a part with 100,000 points. Now there are parts that we use millions of points to describe, for example. So now I want to share some artwork that has emerged from some of our computations, and technically it's science, but we've just been struck by some of the images that have emerged, and I'll do my best to describe that. Again, we're a multidisciplinary center, so while I understand the computer science aspects of this, I am not a material scientist or a mechanical engineer. This image is a model of an alloy that simulates a certain heat treatment to predict the distribution of features in the metal that are relevant in determining ultimately the properties of that metal. And the simulation was run using a GPU, a graphics processor, to do computational work. This is an image of the low-pressure turbine of one of GE's aircraft engines. This was generated out of a simulation that we ran on the Jaguar Cray machine at Oak Ridge National Lab. This is a zoom in on some of the blades. These are the spokes I referred to earlier. You can see some of the geometries there. The colors are a measure of efficiency and efficiency loss through the stage. We refer to this as computer scientists as the Rice Krispies diagram, but our material scientists don't like it when we call it that. This is actually 3 models of nickel-based alloys where we're trying to understand the microstructure of the molecules so that they can provide us with insights into the properties of the metals themselves. This is a simulation that was run on Argonne National Lab's Intrepid machine that's a Blue Gene P from IBM. And this is a visualization of a jet engine exhaust, and it's used to help guide engineering decisions, improving performance and reducing noise. Noise is increasingly an important design constraint from regulations, and it's something that is sometimes conflicting with other design criteria that we're trying to meet. If we took a cross-section of that to look at this in 2 dimensions, it produced this image, and I have this actually blown up to 3 feet by 4 feet hanging outside my office. I think this is just a beautiful image. Okay. So now I'd like to talk a bit about the software and software challenges that are faced in addressing the needs here. So there's an interesting dynamic that seems to come out in the contention between hardware and software. And I show one piece of hardware here on the left. That's a gas turbine. I'll get to in a minute, but I want to start with a quote from Tom Dunning, the director of National Center for Supercomputing Applications, that every congressman likes to sign his name to the latest, greatest machine. These are the supercomputers. That's the photo op. You don't get the same op with software. And we have this challenge all the time at GE in that our communications group or tours are looking for something that they can show people. You can't really show people software the same way you can show them a piece of hardware, like you see on the left side of the screen here. So this was a quote from a past chief technology officer, that real technology makes a sound when you bang on it. And this is a stigma that we've had to overcome in the software world. But we certainly are moving to change and create greater awareness of the importance of software. So if I think about the kind of software I want to run these simulations, as I've shown before, I can draw it out on this diagram. These are called web diagrams. Affordable, scalable, have a well-documented manual training available. I want to be able to port it to different applications. I want it to be interoperable with other packages. I want it to be able to follow my needs in terms of flexibility and to validate when compared to experimental results. The problem is that very few things look like all of that. So if I plot the codes that come out of the national labs, for example, doing weapons testing and such, they use machines very well. They're scalable, they're affordable, they're public domain. They may interoperate a little bit. They certainly are validated, but they sometimes require a PhD to be able to understand how to use. So it's something that we see some needs in, which I'll get to in a minute. Open source software, also affordable, often scalable, and works with other packages and portable, but not, once again, not something that you can typically get training for, and not necessarily something. And these all have question marks after it, and we could debate these for a while. The point here is that these have different shapes. So we look at commercial software, stuff that we can purchase from vendors that are typically called ISVs, independent software vendors. They have validated code. They have excellent training available and are well documented. Historically, their user base has not required it at the scales that we need, and so we've had some challenges convincing them to move to more scalable architectures. Portability represents a cost for them, so they have some, but only as much as their markets push them. Interoperable, they often have no reason to be interoperable because they want you to be locked into their product, but in some places that changes. And affordable, they need to make money. They've made an investment and they have shareholders. And one of the most common pricing models has been to charge by the core. So as we get to these parallel machines that may have tens of thousands or hundreds of thousands of cores, the affordability is a significant challenge with commercial codes. And so there's an open question, how do we get here where we have software that builds out all of these capabilities? And in many cases, the companies like GE have elected to build our own in-house to meet all of these kinds of demands. But that is only possible for some of the larger companies, and there are certain areas where the proprietary advantage of this is not necessarily significant. And so we would certainly like to stimulate the community to produce open source or commercial codes that do meet all this. We also always have a legacy code, and I guess I'm pretty blunt with the visualization here, but legacy represents, on the positive side, all of the knowledge and experience that we have built up over the years, including investments in software, hardware, data, validation, and in that sense, that is what allows us to build aircraft engines that you're confident to fly from city to city on. On the other hand, when we are now, I don't want to use the word stuck, but when we are now tied to these, we do have some inertia as new architectures emerge to take advantage of those, and some things can become obsolete, and convincing people to move off the old way that they did things to a new method is sometimes challenging. However, there are some forcing functions here, and multiphysics is one that we've just never had the computational capability to do that, and it's something that people see as technically interesting that will force us to rewrite some of our legacy systems. An example of this is the interaction between the computational fluid dynamics models and the acoustic models. So think about shock waves in a engine that are created by the flows through there. Acoustics being one physics, and the pressure flows being another. Then, or the temperature flows. The emerging markets we recognize do not necessarily have these legacy constraints and are forging forward pretty strongly, and so that's a competitive threat that we will be needing to address with legacy. So if I had a wish list, I'd like to see the software that we're using be ported to emerging architectures, scale to hundreds of thousands of cores, have a non-CPU-based way of being purchased and supported, address multiphysics and multiscale, as I said there, be able to quantify the uncertainty for the results, have a mechanism for verification and validation of those models, and interoperate with each other, and then have the company be interested in replacing the legacy software where appropriate with such software, and that's our vantage point at present. And if we think about trends in hardware and software, the cloud concept is making hardware cheap, flexible, and abundant. What is driving software to the same kind of form? The cost of building hardware, the first object often is small, and then it takes a lot to produce the plant that's going to mass produce things. We have the opposite dynamic with software, where the first version is incredibly expensive, but then copying bits is very inexpensive. Okay, I just changed. There we go. I had a slight delay in this. So let's talk about impact to GE. I'm sorry, I'm changing slides and it's not updating on. There we go. All right, so I'd like to talk about the size of a couple of these problems. Certainly in genomics, as we think about personalized medicine, where we need to think about sequencing each individual, the human genome is 2.9 billion base pairs. That's a lot of data to store. Now you go across 6 billion people, and that's going to be a lot of data that's going to need to be processed. In the Rice Krispies again, there's to do 100 microns cubed with 10 alloying elements and 100 hours of heat treatment, which is about 100 million time steps, with 8 billion grid points necessary. That is 80 peta operations, and that's per example that you were doing. And that would create a data set that's 1.92 exabytes, or 1,920 petabytes of data per test case that you are trying to do. We have a simulation with water molecules where we would require 9,000 exaflops of interaction per case. If we look at 30 billion atoms, each interacting with 300 local neighbors, with a minimum of 1 billion time steps as we try to model that droplet forming ice to understand formation of ice on things like wind turbine blades or jet parts. The other things in this diagram, there's the jet noise again, the pressure turbine, which I'll talk about in just a bit. So the thing that by and large has benefited most to date from simulation and supercomputing is turbomachinery, and this is both the gas turbines, steam turbines and energy, also wind turbines, as well as the turbines that are used in jet engines. And the kinds of things that we're simulating there are computational fluid dynamics, so this is heat transfer, acoustics, combustion, finite element analysis, so we're looking at fracture mechanics and other material properties. The materials themselves, we need to understand when they're going to break, melt, crack, etc., or even just understanding what alloys we need to produce to meet different criteria for lightness, strength, melting temperature, etc. And we have employed a number of computational tools as shown in these various diagrams to do so. The one I want to zero in on is the low pressure turbine. So if we look at a cutaway of an aircraft engine, which you see here, there's the high pressure part where the high pressure turbine is where the ignition happens, and as it spins, it's linked to the high pressure compressor, which pulls the final air into the high pressure turbine itself, where that ends up blasting out in the final stage is the low pressure turbine, which drives the fan at the front of it, which is the part that you see when you're boarding an aircraft. The low pressure turbine is so important to our criteria because it's 20% of the engine weight in itself, and we'd like to design that down. And even a small efficiency improvement in there has a substantial fuel savings relative to the overall system. So in order to do the simulation that you see described in the bottom right there, there's about 1,000 blades. Those are each of the spokes, and each blade is represented by 5 million geometric points with 9 degrees of freedom, so these are the variables, pressure, temperature, etc. We run 60,000 time steps for that, and that would be 2.7 petacalculations per case. Now that's the ideal. We're not currently running that. We're running something that's a fraction of that. That one would generate a 180 terabyte file as an output file per case. The model that we run now, the file that it generated on Jaguar down at Oak Ridge, took 14 days to FTP from Oak Ridge to the center here. And the same output file from this example I just described would take 2.3 years, just to give you an idea of the download speed relative to the size of the data sets that are generated here. So one of the other things that's going to happen is data is going to increasingly become non-portable. Wherever you run these models is where that data is going to reside forevermore. So wrapping up this part, and then we'll talk a bit about the center and further resources. What the center does in terms of simulation-based engineering and science is looking at the design capabilities that we have for these machines, understanding the physics around them, developing the algorithms and methods and tools that are used in those designs, and then we partner with the businesses to validate them and iterate on those designs. To summarize some of the points I've tried to make through this talk, computational modeling is increasingly parallel, and this is forcing us to think differently about how we formulate these problems. The act of simulation is essential for us being competitive in the modern marketplace. There's many software challenges we need to address, and as we showed in some of our images, science can be beautiful. So to learn more, here are some of the links that the team here has provided. And if you're interested in jobs at TE Research and working in groups like I work with or been in my own group, there are portals here that are shown. And we wanted to make sure you were aware of the next 2 installments of the software webinar series. They will be August 10th and 24th. The topics are as listed here, and 2 of my colleagues will be giving those. And now I will open it up for questions, and Brandon is here as well if you want to talk to somebody who has an account on Jaguar and Intrepid. All right, we have a question for parallel programming and grading cloud. Do you have any suggestions about when to use MPI, MapReduce, or Hadoop? We certainly are looking at MapReduce and Hadoop for some of the big data problems. One of the things that you need to keep in mind is what problem are you trying to solve, and recall where Google developed MapReduce and Hadoop to solve their search problem, and where you're doing something similar to what they're trying to accomplish, it may be appropriate, but for say large volumetric, multidimensional, dense data, that may not be the best model. And I think more appropriate to your MPI question would be MPI versus OpenMP versus the various threads paradigms. And I think what we're seeing is the emergence of multi-grained or multi-scale parallelization, where you may need to look at a combination of techniques where you're going multi-core or to GPU or to multi-node and combining, decomposing your problem appropriately to each of those granularities. Anything to add, Brandon?
I guess the thing I would add is in terms of MPI versus Hadoop and MapReduce, it's a question of coupling. If you have a tightly coupled problem that is doing a lot of math and a lot of work, you're going to want something like MPI. That's what it's designed for. Hadoop and such are much more designed for loosely coupled problems where you're searching large amounts of data. So that's really kind of the way I look at it in terms of deciding which route to go down.
All right, we had a question about what skill do you expect from job seekers to work in your group? I actually find it pretty challenging to find people with a good mix of skills. We need to get about 2 inches deep in every other field. So versatility is certainly one thing. The other is understanding both hardware and software. We've my group actually emerged out of the embedded computing, and we do quite a bit of high-performance embedded computing still. And understanding what's going on down at the low level is, in fact, very useful in tuning the massively parallel designs as well. So having a good background in software and algorithms, as well as in understanding things like memory hierarchy and processor architectures are ideal. Although we do find that we can find somebody very strong in one area and kind of cross-train them in the other areas. Okay, question, are you also looking for considerable experience, or is it possible to learn after getting a job? I just hired a fresh PhD from Johns Hopkins that had purely academic experience plus some government grants that his professor had. So that is certainly an example of somebody that we just hired, a very bright, motivated, hardworking person, not somebody that had a huge depth of experience. But we've also been able to, last year I hired a professor from a university that certainly had a tremendous depth in high-performance computing. I also wanted to mention there's a training program at the center. The GE for many years has had something called the Edison program. This is typically used to train traditional engineers, electrical, mechanical, etc. And there's now a software Edison program as well, and so we bring in people typically at the master's level, PhD level for the center, and in the businesses it can be people who are getting their masters that then go through it's actually a accredited training program. We've worked with a number of universities that have close proximity to GE sites to get it accredited, and it is a way to continue your school, if you will, while at GE. Okay, aside from visualization, what strategies do the teams use for processing and mining the output data for meaningful metrics?
I guess I'll try to handle this one. There's quite a few strategies, but visualization is probably our primary one. Another thing is thinking about your simulation ahead of time, trying to decide what points are there of actual interest, and then augmenting the output to specifically return you the results that you're interested in. Beyond that, there's a wide variety of data mining type techniques that can go on for searching large data sets to find useful information. So we have quite a few techniques, but visualization is always the easiest one to point out, hey, here's something interesting, and then you kind of go back in, extract a smaller subset of data, and really try to get to the detailed answers.
Okay, question about the same Edison program you talked about. I'm an international student on an F1 visa. Do you also hire international students for a full-time job or internship? We do at the PhD level.
Hi, everybody. Unless you have any further questions, we're going to wrap up this webinar. Thank you so much for joining. We have been recording this today, and we will be posting it to our website, which is ge.com/research, where you want to register. And those who were unable, would like to hear this again, you can certainly feel free to go out there and listen to the entire presentation, and it's recorded in entire format. And you can also reach it at ge.com/software webinar. So thank you to everyone who joined. We certainly hope that you enjoyed your time today, and we appreciated the opportunity to speak with you.